So Jim, there you go.
Great, thanks, Brian. And I'm happy to be here with the Semioid Expo. I just noticed I have a whole ton of slides, way too many, so mine will go by a lot faster. I think there is some redundancy, so I'll skip those things from what Tiernan already presented. My presentation here is about a variation of a couple of semioid scenarios that are already present. One of them you just saw that Tiernan and Greg Waterman put together. And then there's another that just came out in the summer that Brody Johnson from St. Louis, Missouri put together that I thought was really nice. In fact, he beat me to it. Last summer and months before that, I was playing around with an idea very similar to his. And then when I went to kind of write things up, I noticed it was already in the Semioid library, which was pretty awesome. So his modeling is similar in that he uses a beam and has students take measurements, very similar to what Tiernan presented. The difference is the beam is made out of metal. And a significant difference is after modeling the beam bending by its own weight, he then introduces a point mass at the end of a cantilever beam, and then uses the direct delta impulse to model that point mass. The students do that. And then because of that non-trivialness, the solution actually requires, say, a Laplace transform to ultimately tease out the solution. And so what I have found is a couple of things I've had some issues with. I've done the beam presentation many times with the model Tiernan had presented. One of the issues I've had, as he pointed out, is time involved and also space. The beams are pretty large and require a bit of space. The other issue is that our system, our courses that we teach at Oregon Tech are quarter systems, so they're shorter. And in our first quarter ODE, we do not cover the Laplace transform. And so the first beam modeling scenario that Tiernan and Greg put together is quite good because it does not require anything beyond integrating polynomials. And the other thing I've noticed over the last year or so is looking at the literature in engineering. And I noticed there was a lot of presentations from classrooms where engineers use what are called singularity functions. This is just another name for distributions, but done in a symbolically rather friendly way, student-friendly symbolic way. So I wanted to go over very quickly how one can solve these problems using singularity functions, as opposed to the variant where we would use, say, the Laplace transform. So the first scenario, we've seen that from Greg and Tiernan, and the idea there is to explore what the solution should look like before actually knowing what the differential equation is. And I think that's really cool that you can see the classification of what type function you think it should be. Students are led to believe that they've got probably a polynomial going on. When you look at these curves, they're certainly not going to be, at least at first sight, you wouldn't think they would be trigonometric or other, maybe an exponential for the cantilever. But ultimately, they come to the idea that to cover all the three scenarios, pin-pinned, embedded, or free, that a polynomial seems reasonable. And then they, as Tiernan suggested that students, they take that data, they put it into a spreadsheet and find that, yeah, actually a 4th degree polynomial looks pretty good. About that 6th degree polynomial, yeah, we found that. I also found students looking at that, but if you look at the coefficients of those, are the 5th and degree coefficients, 5th and 6th degree coefficients are essentially 0. So they don't add much. And then Brody's idea of using a steel model beam, and very similar, taking measurements, and then there's a picture of his beam from his scenario hanging off the table. Looks like it's a 1/2 or 3/4 inch wide steel bar, and he provides the data as well. One way to shorten the labs is just not to have the labs, it's just to use the data that's been measured. For example, the data he presents there and what Tiernan and Greg had put in their simiode scenario. The takeaway, of course, is that I find that the students really like getting involved with things that they can measure and go about taking some ownership in some of the experimentation. And in Brody's, they will be given the model of the differential equation, and then he gives a really nice derivation of the solution using the Laplace transform, and leaves some of the details to the students, the important details, I think, to that derivation. And as I pointed out earlier, our quarter system, the first term course, does not use Laplace transforms, but our second term course does use the Laplace transform. And so my plan is the next time I teach that course, I'd like to bring in either Brody's excellent scenario or a variant that I've been working on, which I call beam deflection light. So here I'm going to use a smaller beam, but it's the same material. And it's not necessary that you have to use this particular type of beam. One could also use a paint stick or a ruler or just a yardstick, something that's relatively easy to handle, cheap, and so forth. And then the idea is to take some mass and put it on the end to deflect. Brody had an idea in his, and I like it. I think I would go with it when I teach using this kind of scenario, is to use bottles of water. It's free, pretty easy to determine the weight of a plastic bottle of water based on the volume of the water. Here's a picture from my old office where I just was playing around with some beams and taking measurements. So I should, if I haven't already said, this is a bit of a work in progress in that I've not had the opportunity to work with my students yet, but I have gone through the experimentation enough times that I feel that it does a pretty good job consistently. So we're going to work with as opposed to Brody's experiment, here we work with a beam that's short enough and light enough that when you support it, it does not bend at all. But then we deflect it with a piece of whatever mass of a known mass. Okay, so singularity functions, what was really interesting for me is I thought I knew about these, maybe thought I saw them, but then when I was reading it, I said, I'd never seen this in a math class, the singularity functions. And I mean, I've seen them, Heaviside function, of course, Dirac delta and others, but I'd never seen them presented in the symbolic way that some engineers do. And so here's our Heaviside function, which is in fact a function. Obviously has a jump discontinuity there at a position L. And here is Heaviside himself. Then you go on to start the ramp function, which is the next one up, bump up a degree. And here we improve the continuity, but notice it is continuous but not differentiable at L. And we can proceed on with further higher degrees, the quadratic singularity function. And these are in fact functions. And notice now we've improved a little further that this function is in fact differentiable as well as continuous. And then the Dirac delta function, we math people put in quotes because we know that it is not actually a function, but symbolically we treat it as one and seem to get away with a lot by doing that. We can make these computations more accurate or more mathematically cohesive by using distributions. And here's Dirac from 1933. So here we're going to model the beam that Tiernan was working with, but instead of a longer beam, we use a shorter beam. And instead of measuring a whole bunch of deflection points, we're just going to measure one deflection. And here's some, just throwing in some other options for types of discontinuous beam loading, where we use those ramp functions and Heaviside functions and so forth. This is beyond what I would do in my math class, just throwing it in there for some completeness. And then a very nice notation for these singularity functions is this bracket notation. And a lot of calculus, the symbolic calculus, turns out to be really easy. Again, these symbolic calculus formulas we can verify using functions of compact support and the distribution theory. And when we integrate, it depends on whether your power is negative or positive. So for the doublet, the delta function where the powers are negative, to integrate, we simply just add 1 down here at the bottom. And for when n is greater than 0, greater than or equal to 0, we just integrate as we normally would. And derivatives similar. Rules are very, very symbolically friendly. And then here's our model. Again, we in this scenario, we're providing the students with the model ahead of time. So they've already, say, maybe done the experiment the term before with either myself or Tiernan, where we're modeling and verifying that, validating that model. And then the several boundary conditions that Tiernan had mentioned. And as he pointed out, if we just have an omega that's constant, where we're not putting a point mass, where the beam is deflecting by its own weight, and assuming that the weight is constant, the density is constant throughout, it's a simple matter of integrating to pick up the deflection at the end. So if we model so what I want the students to end up doing is they're going to take a beam and measure the deflection, and then they're going to solve the differential equation. Now, I haven't decided yet whether I'm going to use these singularity functions or the Laplace transform. That really is something to think about. Is currently in our Oregon Tech math differential equation, singularity functions are not a criteria. But we give ourselves some flexibility in our coursework that we can actually deviate a little bit from our what we call the core criteria. So I'm still debating on whether or not I want to push the symbolic calculus of singularity functions in this particular course. And if I don't, we would just use Brody's derivation, which is just use the Laplace transform. It's a little harder algebraically and computationally with the Laplace transform, in my opinion. That's the selling point for the singularity functions. And so as the students solve the problem, they find the solution to the curve in the middle of the page here, this cubic. I think Tiernan had one similar to that shown earlier. And if we point, and the other thing that is different than what Brody presents in his scenario, a very minor thing, but actually makes the algebra a little easier, is if you set your x equals 0 to be the free end rather than the embedded end, the math just is a little more friendly. So we can measure that deflection. Here I'm just hanging a point mass off the end. One could drill a little tiny hole in that beam to make it a little easier, and could use, as we pointed out earlier, if you don't want to spend a few dollars on some masses from Amazon, where I got mine, you could just use some bottles of water or other items of known weight. So just last night, I did some measurements on my dining room table and found that using the moment of inertia, which is just the base times the height cubed over 12, using the beam itself from Home Depot, this beam here, it's a 1/4 inch thickness and 1.75 inches, 1 3/4 inches in width. And if you crank that out in meters, you get a very tiny number. In fact, that E and I, they kind of interplay, one being a very large number and one being a very small number. And so if you're off just a little bit, that can cause some predictive errors. So here, using that mass and reverse engineering essentially to find E. So that's one of the major variants between Tiernan did discuss that we do some estimation of E using the scatter plot. Here we're just estimating E using a single measurement. And it turns out to be rather accurate, I find. 8.26 times 10 to the 8th works pretty well. And then what I want the students to do is go through and solve the embedded solution, where they're putting a point mass in the very middle at L/2. And what I want them to do is to predict, use their solution to this model to predict what would be the force needed to displace that beam in the middle, say by 1 centimeter. And if you do the math using the solution, you find the students would be able to find that that force is about 12.5 pounds. And then last night, it was a little bit of a juggle to get this done. But there's the beam not deflected at all. And if you look at the ruler here, it's at about 78 millimeters. And so what I did next was grabbed a fish scale, also purchased at Amazon for about $10, and held it while my wife took the picture of the deflection. And it was about right on. It was hard to get that fish scale to register right at 12.5. It was fluctuating. It's a dynamic process there. And so I had her take a whole bunch of pictures, and that one seemed to capture it pretty well. So the prediction actually, the theory works quite well in predicting these kind of deflections. So just a summary of the scenario here. I'd have students, what I'm liking about this scenario, again, is it's small space. Each student can work with, or team of students, pairs of students, however you want to break them up, can work with just a little beam. I used an inexpensive clamp from Harbor Freight, one of my favorite tool places. It was only about $3, but textbooks work well too, calculus books. You can finally get some use out of those calculus books, and then an inexpensive ruler for measuring the displacements. So have them measure that displacement, solve the boundary value problem, either with the singularity functions or Laplace method, and then estimate the Young's modulus, solve the other embedded system, and predict what should happen, and then actually set it up on a table and take a measurement. Once again, I think both for cost, but also it might work just well for the embedded to have two tables near each other, and then hang a bottle of water right in the middle with the known weight. And then go ahead and go a little further, maybe look up online what the modulus should be. We could also supply that modulus, Young's modulus, just from the experimentation we've done, or from looking on the PVC code. Personally, I found that the estimates that we're finding seem to be more accurate than what the Home Depot literature says the E should be. Nicely, there's a couple ways we can estimate. We saw already using a scatter plot and then reverse engineering to get E. Another way to do it, Tiernan mentioned this, is we have a lab here at our college, our engineering school here. And this is CJ Riley, Professor Riley from the Civil Engineering Department. And he took Tiernan and I over there, and you could see the little beam right here in the clamps. And it's a pretty simple device. It's on a threaded, the threaded columns or rods here will rotate and slowly pull that material apart until it breaks. And right before it breaks, it goes into right before it becomes, say, a plastic. It's elastic until it just becomes distorted and then breaks. And the slope of this line, we're looking at stress versus strain here, and the slope of that orange line is computed through the computer on the machine, and that slope is your Young's modulus. And with that machine, they found it's right here in the middle. They found it to be about 6.59 gigapascals, or times 10 to the 8th newtons per meter squared. The single deflection is pretty close at 8.26, and then the online I looked up it's PVC essentially. If you look up PVC rectangular, the PVC material itself, you get a various range of values. So again, I'm not exactly sure of the selling. I love working with these singularity functions. Personally, I found them really nice because of the algebra and the symbolic manipulations were very simple. They're elegant. There's a lot of the distribution theory kind of hidden in the background there, of course. And I liked having less time in the lab. the lab being the classroom, measuring things. As much as I like doing that and have fun doing that, our quarter system really doesn't have the time to be spending multiple hours measuring things. And many of our students are engineering students where they're doing that lab work constantly. Another thought was maybe have a game with the students where the teams compete as to who can predict best what's going to happen with the beam in a various scenario, and then have it measured and see how that works. There's some references. Both the scenarios, simulated scenarios, are posted in at the simulated library, and some of the singularity function stuff I pulled from an engineering lecture from several years back from the University of Maryland. I've got a reference with some stuff with distributions, but that's really it. That's the essence of what I want to do. I've made it work personally myself, but I have yet to get it into the classroom.
Well, thank you. Are there questions or comments from our listeners? I've now heard the word singularity functions twice at this conference, and then I hear the word distribution, and I'm trying to assemble. I mean, when you integrate a Dirac function, you get one, and a distribution is some function which you integrate in probability to get one as well. So is that the essence of what these things are?
Well, it's a little different. In the case of distributions, we're looking at a distribution is a mapping where you start with functions that what we call compact support. So they vanish off of some closed interval, and then they're smooth. And a classic example is this bump example here. And then we define the distribution as a functional from those functions of compact support into the real numbers. And one can then kind of explore the idea of those to come up with what would be an appropriate definition for the derivative in an integral of a distribution.
Okay.
And nicely, with a little integration by parts and knowledge of integrating over improper integrals, one finds all of these things, all this calculus of symbolic calculus of singularity functions is completely consistent and therefore kind of put on more firm ground.
Okay.
So different, it's not the same as a probability distribution. Probably not unrelated.
Okay. So a Heaviside isn't an example because it's over infinite, it's non-zero over an infinite region. Is that right?
No, the Heaviside, the distribution Heaviside, it's the domain of compact support functions, which it's the phi functions here that are of compact support. The distributions themselves are not.
Okay, all right.
In fact, there's one way to give rise to the distribution is just to integrate against those compact support functions.
Okay. Well, I didn't mean to take over, but are there other?
Oh, absolutely.
Questions?
Didn't think that way. No.
Okay.
Are there
other questions? It's pretty clear that faculty can get into the lab and mess around successfully, especially if you're not dealing with electricity, so you can't get shocked. And I think what you two have found is it's nice to be near engineers who have equipment, big equipment for measuring the stress and so forth, and small equipment. And I would recommend that even if you're not near engineering students, you go down to your physics department, equipment technician, and they've usually got all kinds of stuff they'll give to you. My first experience, I went in and he said, do you want a meter stick or a long meter stick? And I went, what is a long meter stick? And it turns out a long meter stick in their definition is 2 meters long. But he kept saying long meter sticks so much that I was fascinated. And I said, show me one. And it was 2 meters long. I said, you mean a 2 meter stick? And he goes, yes. So you learn their vocabulary. You learn about interesting toys that they have that they've never used in years. Some are historical, and playing with equipment is always fun. And you're both right to try things out ahead of time, and and even hesitate when you finally do it to bring that in. So I thank you both, and let's give our colleagues a thank you.